So this is lesson 4.4, projectiles launch at an angle. So question one here is right, this is a do now question. It says, well, as the launch angle gets closer to 45 degrees, well, what happens to the horizontal distance traveled? Right, so let's play this GIF, right? Let's play this GIF. Let's actually loop it and let it's already looped. As you see on the bottom, right, as your launch angle increases, right, as we increase our launch angle and we get closer and closer to 45 degrees, well, you see that my horizontal distance traveled increases. And there's a maximum angle that, well, there's a maximum angle that gives us their farthest horizontal distance traveled, which is 45 degrees. And as we get, again, as we get further away from 45 degrees, right, as your angle increases and gets further away from 45 degrees, well, our horizontal distance traveled also decreases. So we can essentially, from this GIF, from this video, we can assume that, well, 45 degrees gives me my farthest horizontal distance traveled, right? So we can test it going to simulation here, right? So let's go back to the simulation. I'm gonna do this. I'm gonna give myself one launch it. Let's launch at let's actually clear everything, right? So let's launch at 25 degrees. Right, it's 25 degrees goes there. And as we increase our angle, we kind of travel further and further and further, right? So that's 35 degrees and this is 45 degrees. Actually, let's actually get rid of air resistance because air resistance. So that, let's do 35 degrees, right? And let's do 45 degrees. And you'll see that, well, 45 degrees gives me my furthest horizontal distance traveled. And as we get further away from 45 degrees now, right? As we travel further away from 45 degrees, well, you'll see that my horizontal distance traveled, well, it decreases, right? It gets further away as we get away from 45 degrees. So 45 degrees does get you the furthest horizontal distance traveled. Well, what actually happened though is that if you include air resistance, if air resistance is included, well, the optimal angle uh, is at a different angle other than 45 degrees. It's actually the optimal angle of an object. Uh, the first horizontal distance is actually somewhere below 45 degrees, right? If you include air resistance. So it really depends on the object about whether or not how low it is, but if you include air resistance, the optimal angle, the furthest horizontal distance traveled is less than 45 degrees. But if we don't include air resistance, right, if we don't care about air resistance, 45 degrees does give us the furthest horizontal distance traveled. Now, there's another question here, right? So the second question here says, as the launch angle increases, what happens to the time the object spends in the air? And you can kind of reason it by looking at this video, right? As you increase your launch angle, your object actually spends more and more and more time in the air, right? You can kind of estimate it using your brain, right? It feels like it's taking longer because it is. It is. The object spends more time in the air as your angle increases. As your angle increases, and these are assumptions we can make. So the assumptions we can make here are, well, the optimal launch angle for a max horizontal distance traveled is 45 degrees. And the closer your launch angle is to 45 degrees, the farther the object will travel. The amount of time spent in the air increases as your launch angle increases, with 90 degrees giving you the most time spent in the air. So let's do a practice problem here. Let's do a practice problem. Right, so an archer uses a bow to fire two similar arrows with the same string force. And then one arrow is fired at an angle 60 degrees, and the other is fired at an angle 45 degrees with the horizontal. And so compared to the arrow fired at 60 degrees, the arrow fired at 45 degrees has a what? Right, so as we figured out in our assumptions, right, the higher the angle, the longer the time in the air. So they're saying, well, compared to the 60-degree angle, well, the 45-degree angle is what? Well, the 45-degree angle has a lower flight time, right? So it's either C or D, right? So 45 degrees gives you a lower time in the air. But the 45-degree angle gives you the furthest horizontal range traveled, the furthest horizontal distance traveled. So it is going to be C here, right? It is going to be C. Again, the question is asking you to compare the 45 degrees to the 60-degree angle. The lower the angle, the less time, but 45 degrees gives you the furthest horizontal distance. Let's look at 2b. 2b says a volleyball hit in the air has an initial speed of 10 meters per second. Which vector best represents the angle above the horizontal that the ball should be hit to remain in the air for the greatest amount of time? Again, to spend the most time in the air, we need the greatest angle, right? 90 degrees gives us the greatest amount of time spent in the air. And that's the answer, right? 90 degrees. This acceleration assumption is right here, right? So an object is thrown in the air and follows the path shown in the diagram above. Which vector best represents the acceleration of the object at point A? At all points in time, your acceleration due to gravity is downward. It doesn't matter where you are on this path, your acceleration due to gravity is always downward, right? So the only answer here, if possible, is C. And so my acceleration always points downward. My acceleration due to gravity always points downward. So this question says, a football is thrown at an angle of 30 degrees above the horizontal. They give you your initial horizontal velocity. They give you your initial vertical velocity. And the question says, well, draw a graph representing the relationship between the horizontal displacement of the football and the time the football is in the air. So you guys have to realize here that they care about your horizontal displacement. And what do we say about our velocity in the horizontal direction? We said that our horizontal velocity is constant because we have no acceleration, because our acceleration in the x direction is 0. So as time goes on, we have a constant velocity. Well, how do we graph constant velocity on a PT graph, right? We know that slope is velocity. So we know that our distance increases at an equal rate over time. So essentially, this is what our graph is going to look like. This represents constant positive velocity. This is constant positive velocity here. We travel an equal distance over time. Our velocity is constant. At each point in time, we travel an equal amount, equal distance. And so this is what our line looks like. This is what our line looks like. And question 4b says, a football is caught at the same height from which it was thrown. And then the calculate the total time the football was in the air. Let's see, right? So this is essentially the path of the football. You throw an angle of 30 degrees. Let's separate an x and y first. My initial vertical velocity is 7.5 meters per second. My initial horizontal component of my initial velocity is 13 meters per second. We know that my acceleration in the y direction is negative 9.8 meters per second squared, right, due to gravity. And the question says, well, calculate the total time the football was in the air. What is t? What is t? All right. So there are two ways you can do this, right? There are two ways to solve for this. Well, one thing we can do here, right? One thing we can do here is, well, we can solve for our time up to its highest point. right? We can solve for our time up to its highest point in the vertical direction. And all we have to do at that point, once we get the time, is, well, we have to multiply it by 2 because, well, it takes the same amount of time coming back down if it lands at the same height. So if it lands at the same height, we can just double our time up to max height. And so that's the first method. So let's do the first method first. Let's say we're solving up to our max height here, and our final velocity at our max height is going to be 0. Right, so our final velocity at our max height is going to be 0. So final velocity is equal to my initial velocity plus AT. And so final velocity is 0 is 7.5 plus A's, which is this, and then that's T. So 7.5, negative 9.8 T. All right, so let's actually, sure. Let's add 9.8 on both sides. It doesn't really matter what you do. You can subtract 7.5 on both sides. Again, it doesn't really matter. You can do it either way. And now we'll do 9.8 divided by that on both sides. And then I get some number, which I'm going to calculate right now. And I get 0.765 seconds. And so that's my time up. But my total time in the air would have to be 2 times this. So my total time in the air would be 2 times that. I get 1.53 seconds. So my total time in the air here is 1.53 seconds. And that's my total time in the air. That's my total time. And then the second method to solving this question, right? The second method to solving this is, well, instead of taking my time up into the air, I can figure out that, well, it's going to take me some time to erase this. You know, that's good enough. You know, let's not care too much about these random marks. So instead of saying my final velocity is 0 here, because again, we're not solving up to our max height, we're landing at the same height, right? Football's caught the same height from which it is thrown. We can say that, well, that my vertical displacement in the y direction here is 0. And now that we have our vertical displacement, and now that we're actually solving for my total time, what we can do here is we can actually use this formula instead. All right, so D is 0, VI is 7.5 T plus 1/2 negative 9.8 T squared minus 4.9 T squared. What we can do is we can subtract that. So minus 7.5 T on both sides, negative 7.5 T. And then we can divide by negative 4.9 T, right? So negative 4.9 T, we get rid of this T. And this comes out to be, well, I mean, we know the answer, right? It has to be 1.53 seconds. And so that's the answer, right? That's really just one step you could do it, right? That's the second method. And the second method involves you analyzing the entire motion of the football, of the object. And that's one way you could do it, right? So let's move on. Let's do this question now. So you launch an object, right? Construct the cannonball release point. The students measure 0.8 seconds from the time the ball is released. Right? So it reaches the target at a time of 0.8 seconds. It's located a horizontal distance of 2 meters from the release point. So essentially that's dx, right? This is dx. We should probably separate into x and y. Well, I'll do that later. And then the ball, which reaches a maximum height of point P, which is 0.78 meters above the ball's release point. The target is at the same height as the release point. Okay, so they tell you all of this. They tell you your distance up to its max height is 0.78 meters. And the question then says, calculate the horizontal component. Calculate the horizontal component of the ball's initial velocity. Well, we kind of have everything we need here on the x side, right? So we know dx is 2.0 meters, and we know my total time is 0.8 seconds. And the only formula we can use on the x side here, right? The only formula we can actually use on the x side here is actually dx is equal to vxt, right? That's really the only formula you can use. Because, well, our acceleration in the x direction is 0, right? We don't have an acceleration in the x direction. And so if you were to use this formula right here, right, well, this entire side cancels out because, well, a is 0, and then 0 times anything is going to give you 0. So that's 2 is equal to Vx 0.8, and then you divide it by 0.8 on both sides. And then Vx, you're going to get 2.5. You get 2.5 meters per second, right? And that's your initial horizontal component. That's my initial horizontal component. Now, this question right here kind of leads off on the same problem, or rather builds off on the same problem. And so the question says here, calculate the vertical component, right? Calculate the vertical component, Vy, of the ball's initial velocity. So calculate what is Vyi here, what is Viy, your initial vertical velocity. So there are a few things we can do here, right? There are a few things we can do here. We can either look at our distance upward, right? We can either analyze my path upward, or we can analyze the entire path. Let's analyze our path upward, right? Let's say that, well, let's analyze up to point P. And we know that point P, our time is half of our total time, right? Because it goes 0.4 seconds upward and then 0.4 seconds down. And so let's say that our time here is 0.4 seconds because we're analyzing up to our highest point. And at our highest point, we know that, well, my final velocity is 0. That's what we know. And we also know that the y is 0.78 meters. We also know that, well, my acceleration due to gravity, is, in the y direction, is negative 9.8 meters per second squared. So there are actually, can we actually use all formulas? We can actually use one of two formulas, right? So I'm just going to use the first one, which is this. And so final velocity is 0. Initial velocity is one we want to find out. Negative 9.8, and this becomes 4.4, I mean. Plus 9.8 times 0.4. So this gives you negative 3.2. I'm going to add 3.2 to both sides. And so we have 3.92 meters per second. And that's essentially my initial velocity in the vertical direction. And so this is my initial velocity in the vertical direction. The second method is using your entire path, right? Let's say we use our entire path here. We're analyzing our path from the beginning to the end, and we land on our target. And if we're analyzing our entire path here, we can say that my vertical displacement, my displacement in the vertical direction, because I land at the same height, is 0. Which means that if I'm analyzing my total path, well, my total time is 0.8 seconds. We cannot say that my final velocity is 0 because, well, I'm landing at a target here. Well, what we can say is that, well, we can't say anything about my final velocity. So we have this, so we can solve the equation. We can solve this using this formula, right? And this again, this is the second method. D is 0, VI is what we want to solve for, T is 0.8, negative 9.8, and then 0.8 squared, 0.5 times 9.8 times 0.8 squared. So then I get 0 is 0.8 VI minus 3.136. I'm going to add 3.136 to both sides. And then I get 3.136 is equal to 0.8 VI divided by that. And I get a number, right? 3.92, right? Which is what you should expect, right? Because we got that last time. So that's the second way, right? That's the second way. Okay, done. Perfect.